Lesson: Training deep neural networks, backpropagation and optimization. Training deep neural networks involves intricate processes that require a thorough understanding of backpropagation and optimization techniques. These two components are pivotal in ensuring the neural networks learn efficiently and perform optimally in real-world applications. The backpropagation algorithm is central to the training of deep neural networks, acting as a mechanism for updating the weights of the network in response to the error rate obtained in the previous epoch. It involves the computation of the gradient of the loss function concerning each weight by the chain rule, allowing the model to adjust weights in a way that minimizes the error. Backpropagation relies heavily on the concept of the chain rule from calculus, which is used to calculate the gradient of the loss function with respect to each weight. This gradient is then used to update the weights in the opposite direction of the gradient, thus minimizing the error. The process starts from the output layer and works its way back to the input layer, hence the name backpropagation. The efficiency of this algorithm can be significantly influenced by the choice of activation functions, learning rate, and initialization of weights. For instance, using activation functions like ReU can help mitigate the vanishing gradient problem that often plagues deep networks. The role of optimization algorithms in training deep neural networks cannot be overstated. These algorithms are used to minimize the loss function by adjusting the weights of the network. The most basic optimization algorithm is stochastic gradient descent, which updates the weights incrementally for each training example. However, SGD can be slow and may struggle to escape local minima. To address this, advanced optimizers such as ATOM, rm-sprop, and ADAGRAD have been developed. These optimizers adjust the learning rate dynamically based on the training data, the number of epochs, and the performance of the model on the validation set. ATOM Optimizer, for example, combines the advantages of two other extensions of SGD, ADAGRAD and rm-sprop. It computes adaptive learning rates for each parameter by keeping an exponentially decaying average of past squared gradients and past gradients. This adjustment allows the optimizer to perform well on problems with sparse gradients, such as natural language processing tasks. Practical implementations of ATOM can be seen in TensorFlow and PyTorch, two of the most popular frameworks for developing deep learning models. TensorFlow's tf.keras.optimizers.atom and PyTorch's torch.optim.atom provide simple interfaces to incorporate ATOM into neural network training, allowing practitioners to focus more on model architecture and less on the intricacies of optimization. Frameworks like TensorFlow and PyTorch offer extensive libraries and tools that simplify the implementation of backpropagation and optimization algorithms. TensorFlow's computational graph, for instance, allows for efficient computation of gradients, making it easier to implement and experiment with different neural network architectures and training regimens. PyTorch, with its dynamic computation graph, offers flexibility and ease of debugging, which is particularly useful for research and development. These frameworks also provide pre-trained models and transfer learning capabilities, enabling practitioners to leverage existing models for new tasks, thereby saving time and computational resources. In practical applications, training deep neural networks involves a series of steps that include data preprocessing, model definition, training, and evaluation. Data preprocessing is crucial as it ensures that the data fed into the neural network is clean and normalized. Techniques such as data augmentation, normalization, and feature scaling can improve the performance of the model significantly. Once the data is ready, the model architecture is defined, which involves selecting the number of layers, type of layers, and the activation functions to be used. Training the model involves using backpropagation and optimization techniques to minimize the loss function. This process is iterative and may require multiple epochs to converge to a satisfactory solution. During training, it is important to monitor metrics such as accuracy, precision, recall, and F1 score to ensure that the model is learning effectively. Early stopping and learning rate scheduling are techniques that can be employed to prevent overfitting and ensure that the model generalizes well to unseen data. A successful application of these techniques can be seen in the field of image recognition. A case study involving the use of convolutional neural networks for handwritten digit recognition on the MNIST dataset demonstrated the effectiveness of backpropagation and atom optimizer in training deep networks. The model achieved high accuracy with minimal error, showcasing the power of these techniques in real-world applications. By utilizing TensorFlow's high-level API, Keras, practitioners were able to build and train the CNN model with ease, highlighting the practical utility of modern frameworks in simplifying complex tasks. Statistics from various studies emphasize the importance of choosing the right optimization strategy. A study comparing different optimizers found that Atom often outperformed others in terms of convergence speed and final accuracy, particularly in large-scale datasets and complex models. This insight is critical for professionals seeking to enhance the performance of their deep learning models in competitive environments. In conclusion, training deep neural networks is a process that intricately involves backpropagation and optimization techniques. These methods are essential for ensuring that neural networks learn effectively and perform optimally. By leveraging advanced optimizers and modern frameworks like TensorFlow and PyTorch, practitioners can address real-world challenges more efficiently. Practical tools and techniques such as Atom Optimizer, data preprocessing, and model evaluation metrics play a crucial role in enhancing proficiency in deep learning. As the field continues to evolve, staying abreast of the latest developments in backpropagation and optimization will be key to maintaining a competitive edge and achieving success in various applications of artificial intelligence.